Today, I will discuss using hidden Markov models for part of speech tagging. Consider the following sentence: the woman ate the orange. Most people could probably tell you the part of speech of each word in the previous sentence. So the is a determiner, woman is a noun, ate is a verb, the is a determiner again, and orange is a noun. We define the tag sequence for this sentence as the following: determiner, noun, verb, determiner, noun. At first, it would seem simple enough to train a model to build a tag sequence for any given sentence. But let's consider another sentence. I saw the orange cat. In the first sentence, the word orange functions as a noun, but in the second sentence, orange is actually an adjective. It's easy to see that the part of speech of many words is not constant. It depends on the context in which the word appears in the sentence. In part of speech tagging, our goal is to build a model where the input is a sequence of words, that is, a sentence, such as the ones mentioned earlier, and the output is a sequence of tags representing the parts of speech of each of the words of the input sequence. We could formalize the part of speech tagging problem in the following way. Consider a sequence of words, S1 through Sn, and a tag set Q, which contains all the possible parts of speech for a given language. The goal of part of speech tagging is to output the sequence of part of speech tags Y1 through Yn, such that tag Yi corresponds with word Si and Yi is in tag set Q. What makes this particular problem a bit challenging to solve is something we've already alluded to. That's the problem of ambiguity. Many words in the English language can take different parts of speech. Part of speech tagging can therefore be thought of as a disambiguation task. A model that accurately predicts the part of speech for each word in a sentence must effectively take into account the word's context in a sentence. In this presentation, we'll use hidden Markov models, or HMMs, to solve the part of speech tagging problem and demonstrate how they are able to achieve extremely high accuracies. Hidden Markov models belong to a class of models called probabilistic sequence models. So, given a sequence of words, they compute a probability distribution over possible sequences of labels, and then they choose the best label. HMMs require that there exists some observable process whose outcomes are influenced by the outcomes of some unobservable process. So to make this more concrete, in our example, the observable process may be the sequence of words that make up a sentence. We see those and we know what those are. The unobserved process is the sequence of parts of speech. We do not see the parts of speech directly. They are the latent or hidden states that we're ultimately trying to recover. Now I'll talk a bit about the components of HMMs. So the first component is Q. That's the set of hidden states. These states are the different parts of speech of the English language. So for instance, Q will contain verbs, adjectives, determiners, so on. The next is a finite alphabet, which we'll call alpha, and that's the set of words in the English language. So using the set Q, we can define a transition matrix P sub T, which contains the probabilities of one state, that is one part of speech, being followed by another in a sentence. For example, transitioning from adverbs to past tense verbs. These transitions are computed directly from label to training data. Using Q and alpha, we can calculate the emission probability matrix, P sub E, which gives us the probability a word is generated from a given state Q. The probabilities contained in this matrix may be slightly unintuitive, since we're calculating the probability of observing word Si given part of speech Qi. So the probability answers the question: if we're going to generate a word with the part of speech Qi, such as a noun, how likely is it that that noun will be the word Si? These probabilities are also computed from labeled training data. So in the bottom left-hand corner of this poster, we see a graphical representation of an HMM. The top row of states show the hidden states, which are the parts of speech. And the bottom row contains the observed states, the words, which our model assumes are generated from the hidden states. In this representation, only the part of speech one word before affects the current part of speech. So for instance, the verb in the third position is only dependent on the noun in the second, and we see that the arrow from the end points directly to the V, but to nowhere else. So this leads us into a discussion of the order of a hidden Markov model. The graphical model shown here is called an order 2 HMM. So if the order of the HMM is 2, and the model is trying to tag word I with part speech, it will use the tag of word I minus 1 to help tag word I. So the tuple word I minus 1 forms what is known as a bigram, and thus order 2 HMMs are also known as bigram HMMs. So the bigram assumption is shown in the top middle of the poster. The probability of the sequence is a product of probabilities of tag I given tag I minus 1. If we want to consider even more context, we can use trigram HMMs, in which part of speech tags for word I depend not only on word I minus 1, but also word I minus 2. Increasing the order of the HMM may lead to more accurate tags, but also to a much greater computational burden while training. HMMs can achieve remarkably accurate results even when their order is just 2 or 3. So now we have our model specification, and we've decided the order of our model maybe, and we've learned our transition and emission matrices from some labeled training data. Now, given a new sentence, how do we tag its words with the correct part of speech? For a model with latent states like ours, the tag of determining the hidden variable sequence corresponding to the sequence of observations is called decoding. In the part of speech tagging example, the goal is to choose the tag sequence, Q1 through Qn, that is most probable given the observed sequence of n words, so S1 through Sn. For HMMs with labeled training data, this is done using the Viterbi algorithm, which is a dynamic programming algorithm for obtaining the maximum a posteriori probability estimate of the most likely sequence of hidden states that results in a sequence of observed events. The Viterbi procedure for HMMs is shown in the middle of the second column of the poster. And note that the bigram Viterbi is very similar. The Viterbi algorithm begins by setting up a dynamic programming lattice with one column for each word in our new sentence and one row for each possible state. Each cell of the lattice contains the probability that the HMM is in state J after seeing the first T observations and passing through the most probable state sequence Q1 through Qt minus 1. So once we've filled in the full lattice, what we want to do is recover the best estimates for parts of speech. Using what is known as a traceback procedure, we can recover the most probable sequence of parts of speech for each word in the given sentence. So lines 1 through 6 in the algorithm show the process of setting up the dynamic programming lattice, and 7 through 11 show the traceback step. Because we're using dynamic programming, we're guaranteed to find the optimal solution given the training data. Using the Viterbi algorithm, the hidden Markov models that we built here can achieve 97% accuracy in tagging parts of speech, which provides extremely accurate results. So now we've seen kind of the setup. Let's talk about the experiments we conducted to test the efficacy of HMMs. The data we'll be using in this demonstration comes from the Wall Street Journal corpus, well, part of the Wall Street Journal corpus, a text file of sentences containing over 1 million words in total. Each line in the file has exactly one word and exactly one part of speech tag, which was set by a human tagger, presumably a grammar expert. And these tags are taken to be the ground truth. Our test set is a small set of natural text, untagged. We also have a version of the test set that is tagged by a human tagger that is in the same form as the training corpus. So this will be used as our validation set to determine test accuracy. Now, the metric of importance here will be test accuracy. That is, what percentage of words in the test data are labeled correctly by the HMM. We will have 4 experiment types. So we'll test the performance of trigram HMMs with smoothing, trigram HMMs without smoothing, bigram HMMs with smoothing, and bigram HMMs without smoothing. So before I continue, I should talk a little bit about what smoothing is. So smoothing is a linear interpolation technique that protects against overfitting in HMMs. So in trigram HMMs, the final trigram estimate is a convex combination of the MAP for the trigram, bigram, unigram estimates, where the unigram estimate is just a raw probability of seeing a given part of speech. For bigrams with smoothing, the final bigram estimate is a convex combination of the maximi posteriori bigram estimate and the unigram estimate. So here we'll explain the experiment for trigram HMMs with smoothing. All other experiments will proceed in a similar manner. So first, what we're going to do is load in 1% of the training data, train a trigram HMM on the data using smoothing, and then we'll use this HMM to predict on the test data and get a prediction accuracy score. Next, we'll load in 5% of the entire training data, train trigram HMM on the data using smoothing, and we'll use this trained HMM to predict on the out-of-sample data and get another prediction accuracy score. We'll repeat this for 10, 25, 50, 75, and 100% of the data. And this will give us a sense of how increasing the amount of training data increases the accuracy of our model. So now that we know how our experiment works, we can turn to our findings. Smooth versions of the bigram HMM actually outperform their unsmooth counterparts when the training data is small. This advantage decreases as we use more training data. And this points to the fact that bigram HMMs do not overfit to a high degree, so they benefit less from smoothing. When we use all the training data, the bigram HMM achieves 96% accuracy, which is very impressive. Smooth trigram HMMs outperform their unsmooth counterparts by a significant margin. And unsmooth trigram HMMs are the worst performers in our experiments, and they're prone to major overfitting. So all these results can be seen in the plot in the upper right-hand corner. All right, so smooth trigram HMM seems to have the best performance in general, achieving 97% accuracy when trained on the full data set. This accuracy is very impressive. Trigram HMM could probably do better than the vast majority of literate English speakers. As we increase the percentage of data on which we train each HMM, the accuracy improves, but the rate of increase in accuracy tapers off as the percent of training data used increases. So clearly, HMMs are very adept at solving the part speech tagging problem. The accuracy with this HMM model is pretty much identical to state-of-the-art part speech taggers found in most NLP packages or natural language processing packages. So thank you.